Okay, so I'm going to get us started today. I'll talk about Curiosity, and then I'll hand it over, and Alicia will tell you all about Perseverance. So Curiosity is the older of our two active rovers, and it has been exploring Gale Crater for 10 years now. Here's a selfie that it took a year or two ago. It's some of the spectacular outcrops that we're exploring. You'll see plenty more pictures like this. So this is just to sort of whet your appetite. But I first wanted to talk about the goals of the mission. So the goal of the Curiosity mission was to determine, was Mars ever habitable? That was the big main goal. And sort of sub goals underneath that are to look at the biological potential. Were there all the right ingredients for life if it was habitable? Looking at the geology and geochemistry, looking at the role of water in the geology and in making it habitable, and then assessing the habitability in the present day. What is the radiation environment like? What are astronauts going to experience if they go to Mars? So those are the sort of quick summarized versions of the goals. And just briefly, I'll tell you about Gale Crater, where we've been exploring for the past 10 years. This is a very, very large crater with a mountain of layered rocks in the middle. And geologists love layered rocks because every layer means something changed. And so if you find a big stack of layered rocks, you can read the planet's history like pages out of a book. And so we knew before we landed there that there was water-related geology. In the flat floor of the crater, there was an alluvial fan where stuff had washed down from the crater rim. And then we knew in the layers of the mountain itself, there were minerals that form in water, like clays and sulfates. So the goal was to land on that alluvial fan in the crater floor and then drive up the mountain and explore those areas with different minerals. This is just a quick animation to show how this thing landed because it's kind of crazy. If you haven't seen this before, this is called the sky crane. And essentially the spacecraft came down with a heat shield and parachute. And then when it came close to the ground, it cut off the parachute and fired up what's essentially a giant jetpack, hovered over the surface, and then was lowered on a tether to land on its wheels on the surface. And then the jetpack cut the cord and flew away and crashed, leaving the rover on the surface safely. It worked miraculously, even though it looks crazy. It worked really well, and it touched us down right exactly where we expected it to. So we've been on Mars for 10 years. We just celebrated our 10-year anniversary of landing. We've accomplished a lot of the great science. We've accomplished the goals of the mission. We're now working our way up that mountain of layered rocks, looking at those changes. But I thought I would go back to the beginning of the mission and just very quickly go through some of the key discoveries along the way. So one of the first discoveries was driving around on that alluvial area in the landing site where it's nice and flat. We came across rocks that look like this. And if you're thinking, wow, that looks like a busted up piece of concrete, you are absolutely right. That is a big conglomerate of rounded pebbles that were washed downhill and rounded by the action of water and then cemented together into these slabs of sedimentary rock. And by looking at the size of these pebbles, we can tell how much water was flowing. And it was a decent amount. I think it was like knee-high or waist-high water flowing across the surface. So that was one of our early discoveries. We also made a short detour right at the beginning of the mission to this place that we named Yellowknife Bay. And our very first drill hole, some of our first measurements, we actually accomplished a lot of the goals of the mission because the rock here turned out to be mudstones from an ancient lake. And by measuring the chemistry and studying the details of these rocks, we were able to tell that not only were they deposited in the lake, but that lake had water that was safe for life. You could drink that water and not get sick. It had all the chemicals for life, all the things that we know on Earth life needs and uses for food were there present in the rock. And it had organic molecules. That doesn't mean it had actual, little microbes, but it had carbon molecules, which are sort of the precursors to life. So it had a lot of the good ingredients that we need for life in our very first drill hole. But that was just the beginning of the mission. We've come a long way since then. You can see in this picture from early in the mission, Mount Sharp is sort of towering in the background. We've essentially driven there by now. We're climbing up the foothills. As we came closer to Mount Sharp, we crossed this dune field of black sand dunes. A lot of the sand on Mars is black because it's volcanic. And the dunes form these beautiful, they're very aesthetically pleasing to look at. So I like to put them in presentations. But we also, it was a very interesting discovery because of the low gravity and thin atmosphere on Mars. These dunes have sort of medium-sized ripples on them. You can see them all over in this picture that we don't see on Earth. On Earth, we see big dunes and we see the very, very little ripples that go across the surface. But Mars has this medium-sized ripple that also appears. And it's unique to Mars. We don't see it on Earth. So that was kind of a fun discovery. As we came closer to Mount Sharp, and actually most of the way along the traverse as well, we've seen tons and tons of these mineral veins where the rock has fractured and then later water has percolated through and deposited sulfate minerals, and in some cases other more exotic minerals like manganese oxides and things like that, which tell us a complicated story about the history of water, the fact that there were multiple generations of water, because if you have a mudstone that has turned into stone, it's no longer mud, it's a stone. So that the lake was one period of water and now it has turned to stone, fractured, and a new generation of water comes through and deposits the minerals. So you get this complicated story of veins cutting veins and veins cutting rocks, telling you about repeated episodes of water on Mars. As we got into the very foothills of Mount Sharp, we started to see these sorts of rocks. And if you notice, there are layers in this rock and they are perfectly flat. These are more mudstones, just like we saw at Yellowknife Bay, but these are huge stacks of mudstones. We drove through hundreds and hundreds of meters of this stuff, meaning that this lake wasn't just a flash in the pan. It was there for a long time. It was depositing and depositing and depositing. So probably millions of years worth of habitability, not just a brief episode, which is pretty exciting. You know, there are some theories that Mars is only intermittently habitable. And it seems like at least at Jezreel Crater, a very, very deep hole in the ground where water would concentrate, there was a lake for a very long time. So this is an orbital view looking down at the landing site, and the white line shows where the rover has traversed over the past 10 years. So that little jog at the top, that's the detour over to Yellowknife Bay. And since then, we drove down, down, down across the crater floor. I guess I should be using a pointer, huh? Across the crater floor. And these are the black sand dunes that I was talking about. And then in this area is where we started to see those stacked lake sediments. And all through here, as we climbed this hill up to this ridge, it was lake sediments basically the whole time. Occasional little bits of sand dunes, petrified sand dunes in there, but mostly sediment deposited in standing water. But since then, we've spent a lot of time exploring in this valley. This is Vera Rubin Ridge. And we came over this ridge and explored this valley. This is where, in the orbital data before we ever landed, we saw those clay minerals. And clay minerals are really important for the search for habitability and the search for life, because they form in neutral water that's not too acidic, and they are really good at trapping organic molecules. And lo and behold, when we went there and we drilled them, those rocks did have clay minerals and they did have organics in them. So that was very exciting for us to see. Now we are working our way up past that valley with the clays in it, up into these buttes and mesas, and transitioning from the clay minerals that we saw from orbit to the sulfate minerals that we saw from orbit. Sulfates tend to form in more acidic waters, and we think it may represent a drying period where the planet was drying out, getting more acidic, more salty water, maybe less friendly for life, but we're still working our way through those right now. Of course, all of that driving takes a toll. This was actually relatively early on in the mission. You can see already the aluminum wheels had big holes gouged in them by sharp rocks. Turns out the rocks in this landing site were sharper than the engineers expected. And so we've had to learn to be a little careful about where we drive, trying to drive on gravel and sand and avoid the big rocks, even though technically we could drive over them, they're not good for our wheels. So we learned very early on in the mission that this damage was being caused, and you know, the wheels are looking even worse than what's shown here, but they're still working just fine, and they'll last for the rest of the mission. There's no risk there. We just have to not drive over the pointiest rocks we see. So I just wanted to include this. This is a map I made earlier this year, so it's a little out of date. It's from I think January, but I wanted to include this because the color here shows the elevation. And the point is that we're climbing up a mountain. We're not just driving across the flat plain. We're working our way up through the sediments and working our way uphill. So this big label there, we're moving uphill. We're working our way up through all these layers. It's not as obvious in the other image, so I wanted to just include this to show the elevation data. This is pretty cool. This is an image that was taken early on in the mission. It's a little bit false color. The sky is not actually blue. It's been stretched a little bit to bring out some of the details. But this was basically from near our landing site, looking toward Mount Sharp and sort of longingly looking at all this beautiful geology that we might someday get to see. Well, we're there now. For the 10-year anniversary celebration a month or so ago, they annotated this with this little circle here. And if we look at the next slide, this rock is in that circle. And this is a picture from right next to that rock. It's a rock the size of the rover that was barely visible in that previous image. Now we're right up next to it, and we've driven past it since this picture was taken earlier this year. So we're right up in the thick of all of that beautiful geology, and you'll see some other examples of this. This is a picture from that Vera Rubin Ridge, the ridge that was right before the valley with all the clays, looking back down at the landing site. So out here somewhere is where we actually touched down. And then all these black sand dunes and all these mesas of, capping sandstone were sort of in between us and our goal of Mount Sharp. But now we climbed up onto Mount Sharp and we're looking back. And these mountains in the background, that's the crater rim. But I always like this picture because it really, really looks like the Mojave Desert. If you put a train track and a highway across there, you would be hard pressed to say that wasn't Earth. It's a very familiar looking scene, even though it's on another planet. So this is looking the other direction from where that picture was taken, from Vera Rubin Ridge into that valley with all the clays. This is what the surface looked like. It was kind of a crumbly rock, very weak rock. That's why it's forming a valley. It's being eroded out. And it's weak because it has so much clay in it. Clays tend to form pretty weak rocks. And so we spent a lot of time exploring in here, making all the measurements we could of those clay minerals, trying to understand where they were deposited. Turns out it's mostly lake bed deposits. But we spent a whole lot of time there before continuing up into some of these foothills that you see in this picture. So just to remind you again, this is what the traverse looked like. That picture was sort of looking at this area here. And now we're going to start working our way up into the higher levels of Mount Sharp. So this is a close-up. We spent some time driving up onto this flat area. This is sort of a hard cap rock that was formed by sandstone, petrified sand dunes. And it connects with some of those buttes and mesas that we saw lower down as we were just approaching Mount Sharp. It turns out they were actually all one big unit, and now they've been eroded back, and they're just these isolated caps left. So we drove up on that. We were going to drive across it, but it turned out it was made of really, really sharp rocks. They like triangles. So we decided not to drive across that, and we went back down onto this more friendly layered rock that was a little bit nicer for our wheels. But we're working our way up through here. You can see this dark band here. This is what's called the marker bed. This is a very prominent layer in Mount Sharp that we can trace for tens of kilometers, and we can actually trace it all the way around to the southeastern part of the giant mound in the center of the crater. So, that's like 80 kilometers or something, very, very far. And so we just in the last few weeks, we've been looking very closely at that, taking pictures of it, trying to understand what it is, what does that represent? And because when you can trace a bed that far, it's really important to understand it so you can connect all the different parts of the geology together. We were doing that even before we landed at the crater, but now we can get the up-close view of this unit and understand even better what it is. So this is another picture that was recently shared for the 10-year anniversary, but this is just an example of what just a random typical outcrop that we encounter these days looks like. If you squint, you can actually see variations in the color across this outcrop. That means there's variations in the amount of water that was percolating through here. So the minerals are changing even across the face of just one outcrop. You can also see this is shot through with cracks with those minerals in them. So again, that story of the multiple periods of water. And so we're surrounded by this beautiful geology everywhere we look, and we're doing our best to capture it while also continuing to move, which is sometimes a challenge for scientists. We want to sit and stare at the same outcrop forever, but there's a lot more to see. And so we're always trying to balance that, taking enough data, but then moving on to see the next thing, because the next thing is going to be exciting as well. So this is part of a 360-degree panorama that was taken a month or so ago. And we're in this area where the minerals are changing from the clay minerals to the sulfate minerals. And we see that in the layers of the rocks as well. We're going from, we had lots of lake deposits. Now we're in more dry environments. We're seeing stream deposits. So some of these resistant ridges are similar to that stuff we found early on in the mission, those conglomerates, where we're seeing things that are deposited in flowing water rather than in standing water. So a little bit higher energy environment, but less water involved. But those are starting to transition into purely wind deposited sandstones, petrified sand dunes. And so as we climb up the mountain, it's kind of gratifying that we're seeing what we expected, that we're seeing the rocks are agreeing with the minerals and sort of telling the story about how it used to be wet and it's getting drier as we go up, and up is to more recent times. And I had to include this. This is a picture of our 35 drill holes over the course of the mission. It's, this is very early. This is back at Yellowknife Bay and all the way up to present day. You can see one was taken during a dust storm. That's the dust storm that unfortunately finished off Opportunity. But Curiosity was nuclear powered. It survived that dust storm and was actually able to drill a hole and work. But all our pictures are very orange from those few months when the entire planet was covered in dust. But the other thing you can note is all of the different colors that you see, not just because of the dust in the atmosphere, but the rocks themselves are different colors. And when you drill into a rock and out comes gray, that means that the iron in that rock is not that oxidized. Whereas if you drill into the rock and you get a bunch of red out, that's hematite, that's oxidized iron. So that, just looking at the color can tell you what has happened in that rock, the amount of water that rock has seen. And so the fact that we were getting so many gray drill tailings, gray samples, was actually very exciting and revealed that these rocks were, they were not as oxidized as you might expect on the red planet, where everything looks like it's oxidized. Once you brush below that dust, these were rocks that were not oxidized when they were deposited. So that was exciting. And so we're continuing to collect drill samples as we work our way up the mountain, trying to piece together the geologic history. By taking the drill samples, we can actually take some of that powder and put it into the instruments inside the rover and measure the minerals, measure the organic molecules. And so that's when we really learn all the details about the rocks. When we take pictures or zap them with the laser, we get some of the information, but we really need those laboratory instruments to get all the details. So I'll finish with this beautiful picture from just a week or two ago. This is a beautiful panorama put together by Thomas Apperet, who is not on the team. He's an amateur, but amateur is not really the right term for people like this. They're so good at what they do. They process the pictures way better than I could, and I'm on the team. But he put together this beautiful panorama showing where we are and looking ahead to where we're going. We're working our way through these big mesas. Looks like Sedona here. Working our way through these mesas up higher and higher into the mound and looking at some of these other transitions in the rocks that we can see from orbit. So that's where we are right now. And then this is a picture from just over this past weekend from our navigation cameras, just to show you, this is hot off the presses. There's probably a few pictures newer than this one, but not many. But we're working our way through. The scenery is beautiful. The geology is amazing. So lots more to go. It's been 10 years, but we've got a lot more science to do in the coming years. So I'll stop there and I'll hand it over to Alicia. I see one question. Do we want to do a few questions now and then switch over?
Yeah,
okay.
I can do a couple of questions.
Okay, yes.
Just wondering if you have the capability of
dating any of the layers? Yes. The SAM instrument, the sample analysis at Mars, is one of those internal instruments. It was not originally designed to date these layers, but the scientists on the team figured out how anyways. So what they did is they actually took a drill sample right next to a cliff that had been eroding back, and they were able to date that sample and tell how long it had been exposed to the surface based on the amount of radiation that was hitting it. That changes the chemistry of some of the things in the rock. And they were also able to figure out the age of the rock. I'm terrible at remembering exact numbers, but I think it was over 3 billion years old as the age of the rock, but the actual exposure age, the amount of time it was exposed to the surface, was more like 100 million years. So it was young. Yes. Yeah.
When you had that overview, the
I don't know for sure, but I would guess these are probably a couple 100 feet tall. Yeah, it is kind of weird because this is a 360, so it wraps around. It's kind of a fisheye view, but yeah, they're pretty big. They're respectable sized buttes and mesas. Yeah, okay. Well, we'll there's a whole other rover to talk about, so we'll do that and then we'll come back. Okay.
All right. Moving over to Perseverance, which hopefully you can see has a lot of heritage from Curiosity, and Ryan has just really set the stage perfectly. The mobility system is the same. It has the same kind of robotic arm. The instrumentation is a little bit different, and the goals are a little bit different. So we'll talk about that. This is the selfie that Perseverance took in front of the first rock that we collected samples from. So if you can see, this rock here has 2 boreholes in it from the first samples we collected on Mars. Of course, those selfies are taken with the camera that's on the end of the robotic arm. So the rover kind of does this, and then we stitch them all together. Yeah. Okay, so the big deal with Perseverance is that it's part 1 of Mars sample return. We have since the 60s been sending spacecraft, and since the 70s been sending landers to Mars to explore and rove, but we've never brought anything home from Mars. And if we ever want to send humans, we better figure out how to bring rocks back first, right? Okay, so obviously we're going to characterize the geology. That's very important to telling us about, you know, the depositional environments we're working with and about the past climate on Mars. Ryan has already gone through, we know that Mars was a much wetter planet at some point in its history, not maybe, you know, covered in oceans like Earth, but we have lots of evidence of standing water for significant lengths of time now, which requires a different climate than the climate that's on Mars today. We want to look at the habitability and look for evidence of past life. I outline number 3 because that's a big difference, right? This rover is actually the rover that's collecting samples. So the instrumentation on the end of the arm is a drill that collects samples and then stores them underneath the belly of the rover. And we're preparing for human exploration. There are several experiments on this rover that are directly getting at paving the way for human exploration. So this is the testbed rover at JPL. So it's a 1-to-1 scale model. It's pretty big. I mean, it's the size of a small SUV. I just got to go see it myself in June and was kind of overwhelmed, even though I've seen pictures of it a million times. And I wanted to show you, these are the different drill bits that we can exchange to collect samples. Because before we collect a sample, we actually, I hope you can see that, we scratch a little window into the rock, which we call an abrasion. And that's only about 5 centimeters across. But then we can put all the instruments in there and study, you know, the fresh rock instead of the weathered surface. And that helps us to learn everything we possibly can, get all that context information about the sample that we're collecting. So then there's a hole that's only about 2 centimeters in diameter. The samples we collect are really about the size of your pinky. They're only about 1.5 centimeters in diameter, like the size of a piece of chalk, if you remember when we had chalk in schools. Okay. So, and then of course we have the cutest little helicopter in the solar system with us, everyone's favorite, Ingenuity. I'll give you an update on the latest with him too. I just want to throw this graphic up here because you don't see there's a whole subsystem underneath the belly of the rover to store and process the samples we collect. It's like a robot within a robot. It's really complex. So the arm itself exchanges bits with a little piece that's on the front of the rover, and then underneath the belly is this whole subsystem and a separate arm actually that's moving those samples around to seal them for storage, measure the volume, take the final images, and then store them until we decide to set them down on the surface, which is coming up soon for the first round. Just a quick planet-wide perspective of, since the Viking landers in the 70s, where on the planet we have landed landers and rovers. So Curiosity, which Ryan was just telling you all about, is here, and there's Perseverance. I started my career on Spirit and Opportunity. So I spent a long time on those parts of the planet as well. Okay, so the landing site selected for Perseverance is Jezreel Crater, another crater. They punch holes in the surface for us where we can look at layers, so they're pretty handy. But this one in particular is special because I put some blue arrows on here to show you. This is Jezreel. It's about 45 kilometers across, has this inflow channel here that formed this delta. So that delta is pretty special. I mean, it's, you know, obviously flowed or formed by water that flowed into this crater and deposited sediments. But even more spectacular is that there's an outflow channel to the east. So that tells us that not only was there like a river flowing to form this delta, but there was standing water, a lake, that had to have enough water in it to actually breach the other side of the crater and flow out. So a significant amount of water, like we just heard about in Gale. And this is just an edge-on view of the delta. The landing was the same system that was used by Curiosity. So Ryan showed an overview. The difference with Perseverance, which was historical, was that we put all these cameras on Perseverance so that we could actually video our landing this time. And if you have not seen the landing video in its entirety, I can't recommend that enough. You can just pull it up on YouTube and watch the whole thing, but it's pretty spectacular. This is the rover being lowered from the sky crane on the cables. So this is looking down at the rover. This is looking up at the sky crane. And this is looking down at the ground, all the dust that's being kicked up as we're coming down from those retro rockets. So these are off-the-shelf cameras that they kind of last minute decided to add on so we could try to capture the landing, and it was just amazing. So can't give a talk without including some of that. Okay, so this is the actual landing site now. This is the orbital view. The yellow star is where we touched down. This is the edge of the delta. So in between where we landed in the delta is this area here. I don't know if you can see, hopefully you can. There's a bunch of ridges that go this way, and it's covered in sand dunes, and it's really rough. It's too rough for the rover to cross. So we knew from landing that in order to get to the delta, we would have to go around. But before that, we spent literally the first year of the mission, so Sol 0 through 380, on the crater floor campaign in this box. So I'll give you the highlights of that. This is the same map, except now the colors are the geologic map. So the colors represent different geologic units that we had mapped already from orbit. And just to point out that where we landed is right on the border of these two units, which was a cool opportunity for us to get to investigate both. This region is called Seta, which is Navajo for amongst the sands. And I said it was too rough to cross, so we actually had to go all the way down here and find a little place where we did what we called a toe dip. We'll just go in a little bit so we can see those rocks. So these are important rocks to visit and sample because they're the oldest rocks we're going to see in Jezreel Crater. They teach us about the history of the crater before the delta formed. And then when they're returned, because they're igneous, we can use them to get dates on for radioactive dating, and they will tell us more about the paleomagnetic environment of Mars when they formed. Okay, so those rocks, those two units, the tan one is called the Moz Formation, and this one is called Seta. So Moz first. Moz is actually Navajo for Mars. There you go. So this is what those rocks look like. They're igneous in composition, and they have lava flow textures. They're old lava flows. So hopefully you can see kind of this ropey texture, which sort of looks like a Pohoyhoy lava flow. They have pits in them. So these are igneous rocks on the crater floor. And this is the Seta Formation, which is special because it is rich in olivine, which is a mineral that tells you something about the maturity of the magma. And it's also special because, like, on Earth, olivine doesn't last long. It breaks down and gets altered pretty quickly in the presence of water and the atmosphere. So to find a rock that's just chock full of these nice olivine crystals, which you can even see individual crystals in this image, which is a close-up of some of these rocks, is telling us a lot about the environment. So these are igneous rocks. This is a busy slide, but I'll take you through it. So the yellow star here is our landing site again where we touched down, and this is our traverse during the crater floor campaign. So the blue circles on here are everywhere that we abraded or collected a sample of the Moz Formation rocks. And these green circles here are where we abraded and or collected a sample of the Zeta Formation rocks. And so these are on this side, the results of our sampling efforts in the first year of the mission on the crater floor. We double sampled for a reason, because we're going to deposit 2 caches on Mars. And so until we deposit the first cache, we're taking double samples. So we have 1 in each cache. Anyway, these are what those samples look like. And so again, this is only about 5 centimeters across, and these samples are only about 1.5 centimeters across. But you can see individual grains and textures, and gets, we have a lot of studies already about what the composition of these are. Okay, so when we finished at the crater floor, we had spent a year here, and we haven't even gotten to the delta yet, right? The good stuff that we came for. So the project was like, hurry up, get over there. So we entered this phase of the mission we call Rapid Traverse, which is get over to the delta quick. And so we did not take a lot of time to stop and sniff rocks. We really just had to get over there. And so we ended the crater floor campaign around here on 380, and we had to do this whole big old, traverse around Zeta to get over here, where we would then start exploring the layers of the delta. So we actually did that in 40 sols, and we drove 5.5 kilometers, that is awesome. This rover can actually move a little bit faster than the other ones we sent, just because of updates in our software and stuff. But that is putting the pedal to the metal, as it were, on Mars. So I just wanted to include those. Some of the mosaics from that trip are some of my favorites. So this is taken from this position here, looking across towards the delta. So you can see the awesome, layers of the delta front. This is actually the rim of Jezreel Crater in the background. And I love this one because it has even a view of the valley. That's the inlet channel where the water flowed in to form this delta, Neret Babalis. This is my very favorite of the mission so far. This is taken from up here, looking back to the east at this big promontory that's called Santa Cruz. I love the rover tracks here across the plains. And this is Port Angeles Crater, which is this crater right here, and another unnamed crater. It's actually smaller, it's just closer in the picture, so it looks a little bigger. And then one more from this location, looking up at this big lobe of the delta, which we named Miner's Castle. So now we're looking at these sedimentary layers that were formed from, making up the delta deposits from the water that was flowing into the inlet channel. And if you look at this little bitty bright dot in this mosaic, we zoomed in with the super camera, and you can see these are big boulders, but this is the mega version of conglomerates that Ryan showed you on Curiosity. They're rounded. These boulders have been carried in water and deposited in these sediments, and that boulder itself is like 1.5 meters across. So just want you to think about the energy required, the kind of flow that is required to move things that big and make these deposits. Okay, so here we are now in the Delta campaign, which this is our rover tracks. We've been all over the place here, trying to pick the best places to sample the Delta rocks, the sedimentary rocks. So I'll just draw your eye up to the top first. These layers in here are the sedimentary layers making up the Delta that we're very interested in looking at from biosignature, preservation potential, and sampling opportunities. This particular layer right here, we called the bacon strip. Can you see why? We called it that forever based on this image until we actually got there and gave it a real name, which is Hog Wallow Flats. And then Rocky Top right above it. And that's what this looks like. So here, this is the bacon strip up close, Hog Wallow Flats, those layers. And this is right underneath the Rocky Top, which is this here. So now you can see we're looking at really nice, sedimentary layers deposited in water. or from water movement. And we've had 2 successful sampling activities here. So we sampled up here at a place called Skinner's Ridge, and right here. The reason this rock is so bright is because we sampled it and it's been all disturbed. So this is a summary of what we've done so far in the Delta. We've collected 4 samples. Sampling in the Delta has been tough. I'll tell you, we've had a few attempts where when we went to do the abrasion, the rock totally crumbled underneath just the abrasion. So we knew that those rocks would not be competent enough actually to take a core of. So we've had a couple of starts and fails on collecting samples. And so this is what we have right now. And you can see like, this is a really fine grained sandstone. And this is a coarser grained sandstone. They're pinkish in color, which tells you they're oxidized. There's hematite in there. And the berry hollow actually is rich in sulfates, and the most organic material that we have seen so far. We've detected organic chemistry in all of the rocks to some degree, but this one is definitely the most concentrated. So that's exciting. So right now, where Perseverance is back down here at Enchanted Lake, trying to find a place to sample in these rocks. That is literally what we're working on this week. And so this is the outcrop in front of us at the moment, down there at Enchanted Lake. And this is the abrasion patch. This image just came down Sunday. So this is literally the rock that we're working on right now, hoping to sample. So I'll get to update my graphic here, hopefully real soon, with some more samples. All right, I wanted to take just a couple of minutes to tell you about Kodiak, everyone's favorite. It's a favorite on our team. It's the landform that gets imaged the most. It's pretty spectacular. It's this little nub right here. And before we landed at Jezreel, the hypothesis was that this was the delta remnant. So it could be telling us about a previous extent of the delta because it's the same elevation, it's similar. That was our going in hypothesis. Here it is on the cover of Science Magazine just last fall, because it's spectacular. So when we got there, this image here was actually taken from like 2 kilometers away, but we can zoom in and use the SuperCam camera as well to really get at the structure of these layers. And so scientists on our team were able to use that structure to show that this is in fact a delta deposit. Its structure is absolutely consistent with what we see in delta formations on Earth. And not only that, you can use the elevation of that break and slope to determine the previous lake level that this was flowing into. So if you fill in Jezreel Crater at that elevation marker with water, that's what it would have looked like when this landform was being formed. So that was a pretty excellent finding, not too long after we got to the surface, and that's why it got to be on the cover of Science Magazine last fall. Okay, atmospheric science, because Mars is a windy place. That is the main thing happening on Mars these days. Dust devils are very common on Mars, especially in the right season, and you can't help but image them. Actually, they photobomb our images all the time. But this is cool because we actually were taking a series of images in different filters, and so we caught the dust devil moving across the scene. That's the rim of Jezreel Crater back there. So that dust devil is about 35 meters in diameter, which is large. And the helicopter this guy is amazing. Just this past weekend, Ingenuity finished its 33rd flight. It's flown about 7.5 kilometers, which is incredible. It was really sent to just be a technology demonstration. We've never done controlled flight in another planet's atmosphere ever. This is the first time, so it made history. The rotors are huge. It's like a meter in diameter, but it only weighs 4 pounds. Tiny little guy. And it has to spin way, way faster. The RPMs are much faster than required on Earth because the atmosphere is less dense. But it's proven that it'll work and we can do it. It'll obviously be a great tool that humans can take with them. And now we are using Ingenuity that way. It's supporting operations, it does scouting for us. And so it's just been really successful. What I wanted to show you is this cool little video. I'll play for you. It's very short, but it shows you dust lifting on the surface when we fly that helicopter. We have several movies of the helicopter flying. This is the original movie with no processing. This one is different, just so you can see the dust move. And this is the two of them together. And hopefully we can play it a couple times. It's short. So you can see when it takes off, how it's lifting all this dust off the surface. And then the dust gets carried away in the breeze to the left of the image. You know, it's going this way. I'll play it one more time. Unfortunately, we don't take movies every time the helicopter flies. Sure wish we did. It's hard to sequence, and sometimes the helicopter is pretty far away from us. And it's very data intensive to take movies. All right, let's go to the next. Okay, so what we're up to next is we're about to take our first Regulus sample. So that's soil on Mars. It's the loose unconsolidated material. So we'll be doing that in the coming months. And then we're going to Three Forks area, which is basically a big parking lot on Mars. And that's where we're going to set down the first cache of samples. And there's actually a workshop going on this week in the NASA community where we're discussing which samples we're going to set down and how this is all going to work. And then after we do that first depot, we're going to drive up onto the Delta to do the next phase of the mission on the Delta top. So that is what's coming in the next 6 months. And then I'll leave you with this awesome image that the helicopter took of some of our landing gear crashed. This is the back shell and the parachutes. Thanks.
Okay. Who do you want to pick questions? Okay, go ahead.
No, it doesn't. Oh, he was asking about the presence of olivine crystals and whether that makes this rock a palisite. That's a meteor. Right. No, this is from a melt body. Mm-hmm. Well, olivine is on a spectrum between some are more iron rich and some are more magnesium rich, but olivine crystals are pretty dense. So they form first in a magma and then settle out to the bottom. So we think that's what we're looking at.
Yeah, pallasites form at the boundary of a planet's core and its mantle. Right, so they're made of metal. These rocks they have no native metal in them. They are igneous rocks. Yes, in the back.
Since nobody's out there with a Sharpie, how do you know when and where you collected each sample that's going into the sample tube?
How do we know?
You showed the other valley where the sample tubes are being collected.
Mm-hmm.
So how do you know the location and time of each one of those samples? Or do you need to know?
Well, we know when we repeat the question. How do we know where we have collected those samples? Okay, well, we know where we are all the time on Mars. It's a whole effort of localizing ourselves every single day. So we know exactly where we are, and actually each one of those sample tubes has a serial number on it too. So once we seal them up, they have a number on them, and then we actually know which slot it's stored in as well. So we can pull out the ones we want.
We even actually shoot the sample itself with the SuperCam laser with a pattern of dots, so we know the orientation it was in the ground before we picked it up. So we keep track of everything.
We try.
Yeah.
So what have you learned so far about that dark harbor bit?
So I should know better than I actually do. I believe it's turning out to be just a really clear layer of sandstone. We have some ChemCam images and some mass cam images of the edge of the marker bed, and it's got those diagonal beds in it that are sort of the hallmark of just sand dunes. So I believe that's what it was. So don't quote me on this because I haven't actually been following super closely, but I think it's a sandstone, and it just marks a place where there was erosion for a while, and it sort of just made a nice layer, and then things continued to pile up on top of it. Let's see. How about? Okay.
That's a great question. I was anticipating that one. So the design has changed. Oh, the question is, how are we going to get those samples back from Earth? So Mars sample return is in design phase right now. They're not going to use a rover anymore. They actually have a lander. And because Perseverance is doing so well and they expect it to last every bit as long as Curiosity, 10 years plus, the plan is for Curiosity to drive up to a lander that is, or sorry, that's a occupational hazard. Okay, the plan is for Perseverance to drive to a lander and actually hand off the samples itself. So they're designing some kind of exchange, the details of which are being worked out. And the backup plan is to actually use fetch helicopters. But because Perseverance is doing so well, it is now front and center in delivering the samples. So the sample depot that we're about to deposit in the next couple of months is actually the contingency cache. So it's the backup plan that if something were to happen and Perseverance didn't last so long, these samples would be deposited and fetch helicopters could get them. Otherwise, we're carrying samples beyond, and we're going to collect more up on the Delta and keep going and meet up with a lander in the future to deliver. That's the primary method. Karen.
Love all the creative names you use. Can you share with us your naming convention for all those names?
Sure. So before the rover, the question is, how do we come up with the names? Before these land, the team actually does a lot of mapping from orbit to understand the landing site, and we divide that into quads, just like you would on Earth in geologic mapping. And for Perseverance, they were all named after national parks around the world. And so while we're in that quad, actually, during the mission, we use names that are in theme with that national park. So Perseverance happened to land in the Canyon de Chelly quad. How cool for us here in Northern Arizona. So while we were in the Canyon de Chelly quad, we used the Navajo names for all of our targets. And we actually worked with the president of the Navajo Nation to get an approved list. And it was a really cool opportunity and partnership and lesson for everyone in the team to learn how to pronounce those words.
Yeah, Curiosity works in a little bit of a similar way. Likewise, the landing site is sort of divided into a grid, and we name things in one square of the grid based on a theme. Curiosity's themes are just famous geological provinces in the world. So we went through a whole Scotland area, we went through an Australia theme, but once we're in there, we name it after small towns and things like that within that general area of the Earth. So there's lots of small town names on Mars now. Yeah.
What's the distance of the need to travel or expected travel?
What is the distance that the rovers have traveled since they landed? I believe for Curiosity, we're up above 28 kilometers now, which doesn't sound like that much in 10 years, but we've been climbing a mountain, so it's not bad.
You have wheels that are struggling.
Yeah, and the wheels are falling apart.
Which, by the way, Perseverance was able to learn from. The wheel issues happened early enough in that mission that for Perseverance, they redesigned the material for the wheels. So we aren't struggling yet. And Perseverance has driven, I think we haven't hit 10 kilometers yet. I think that we're around 8, 9, it's got to be in there somewhere. Jacqueline?
Oh.
Sample pickup is, pickup, I don't have in my mind. Return to Earth, so similar, it would be the early 2030s, so a decade from now. We got to design the spacecraft and the system, and you can't just go to Mars whenever you want. You have to wait for those launch windows to come around, and it takes 6 months to get there, and then it takes 6 months to get back. So it's slow.
Yes. The question is, how does the data that we've collected compare with the data that the Chinese have collected? You mean with their rover that's currently operating? I don't know. They don't share a lot of their data. So other than some selfies showing that they had a successful landing, I haven't heard a lot about scientific results from their mission yet. Have you? Okay, yeah, so I wish I could answer, but we don't know yet. Yes.
Two questions. One is, what's the maximum depth of Jezreel Lake?
First question is, what is the maximum depth of the Jezreel Lake? I do not remember.
Me neither. And actually, I don't think we can answer that. It's a complicated answer. Because this lake level is actually, we think, as it was drying. And this is the lake level when the Kodiak remnant was formed. And until we understand really the architecture of the delta lobes, we do have the outflow and what the elevation of that is, but there's another question of the age of the lava flows, and did those come, like the floor that is the floor now may not have been the floor, right? There's some complicated relationships to work out there.
And the tracks,
Mhm.
little circles, are those days, individual days?
Those are individual stops where the rovers stopped. So in between each dot was one drive, essentially. Yeah. Yes, right here in the second row.
What is your best guess on the source of the water? Underground or?
So the question is, what is our best guess on the source of the water? I would say we know some of it was flowing over land because we have the channel going to Jezreel, so that was a river flowing. Likewise for Gale, that alluvial fan is fed by a branching network that goes up into the crater rim, so that was flowing over land. At Gale, we know there was also groundwater because those fractures are from water coming up through the ground. But the source for most of the lake, it's hard to tell. Probably a mix is the sort of cop-out answer. But we know some was flowing over the land because we see those river channels. Rain or snow melt. Yeah.
Possible. I mean, these are the questions we want to answer. We know that Mars had a warmer, wetter past, and it had to have more of an atmosphere than it has today. But this environment that we're searching in, and Gale too, these are some of the oldest terrains on Mars. They're over 3 billion years old. And of course, Mars doesn't have plate tectonics and atmospheric stuff going on to resurface the planet. So we're able to see ancient terrains like this. And I had another thought about the depth of the lake, that at least the height of the delta, the sediments forming the delta lobe, ranges from 50 to 70 meters high. So that's a lot. Okay. Yes, ma'am.
Does the rover use AI when it's driving itself? How far does it go before it stops?
She's asking if the rover uses AI to drive, and it uses machine learning. And the reason Perseverance is faster is because it has a whole computer dedicated to that, its own processor, which Curiosity and the other rovers didn't have. But what it does is takes images of the terrain. We tell it, we want to go this far, and we program in safety, like don't go over any rocks this big, don't try to go over any slopes this steep. And so the rover goes for a while, and then it takes images and makes a new mesh. It makes a new map on board, and then it's able to calculate safely how to maneuver. So yes. Do you want to say anything else about that? Or?
Not really. I'll just say, yeah, that's why Curiosity can't go as fast. It can only drive as far as it can see very clearly. And Perseverance can drive a little farther than it can see because it can take new pictures and interpret them on board.
We have 2 more minutes for questions. So
Okay.
there's time.
Yes.
Alicia, I think you mentioned something about paleomagnetics at the beginning.
Mhm.
What kind of study on your samples can you do right now, or does that all have to wait till it comes back?
Has to wait till it comes back. The best labs in the solar system are on Earth. So we need to bring those samples back to answer a lot. And I think in general, even though we're searching for evidence of life, the burden of proof for that is high, right? And we're not looking for critters. We're talking about microbes, just like early life on Earth. And the evidence for that is going to be hard for us to say definitively with what we can do with this rover. And that's why we want to bring samples back.
One of the questions was all this rain or this water events, cyclical events that you're saying, how long ago did that end? And there's no way that this could ever happen again, right? There's no mechanism that anything like that could happen again.
I mean, I hate to say impossible, but the question was when did the water activity stop on Mars? And is there any chance it could happen again? And I think the answer to that is probably no. I don't have a good grasp on how long ago. But flowing water, liquid water on the surface, I think over 3 billion years ago.
Yes, with occasional more recent activity here and there, but really long sustained water is probably 3 billion years, and then more recently we see younger things like alluvial fans and stuff they're not quite that old, but it definitely tailed off after about 3 billion years.
Well, it is 6 o'clock, and so if you have more questions for Ryan and Alicia, stick around. They can hang out for a little bit, maybe. Thank you, Ryan and Alicia, for your presentation. And thank you all for coming to More Festival. Oh, hi, my name's Greg Vaughn. I work at the USGS also, and I'm also I work with the board of directors for the Flagstaff Festival of Science. And thank you all for coming. And yeah, I'm her husband.
So I worked